Hello everyone, and welcome to this Arcteq Wednesday webinar. Today's topic is how to configure automatic voltage regulator function in AQ-200 series devices. My name is Niko Muotio, and I work as an application engineer in the technical support team. You will find a link in the description below to a presentation that goes through all of the things that you will see in the video today. So, automatic voltage regulator function, short for AVR, is used for secondary voltage control in transformers that have an on-load tap changer. It raises or lowers the secondary voltage based on bus voltage measurements. The actual voltage controlling happens in the tap changer. Increasing or decreasing the secondary winding increases or decreases the output voltage of the transformer. Transformer secondary voltage and bus voltage may vary based on changes and variations in the load. The aim of using this function is to keep the output voltage stable so that the voltage doesn't raise dangerously high or unusably low. This function is included in two device types in 200 series. In AQ-T215 voltage regulating IED, this function is included by default, but in AQ-T257 transformer differential protection IED, you will need to define when ordering that you want to have this function included. There are quite a few things that you need to set up when configuring automatic voltage regulator. And we are going to go through these one by one, starting from voltage measurement settings. We go to measurements, transformers, and VT module. So this is the voltage measurement settings for the voltage transformer. And there, first we have the voltage measurement mode. So here we define if we have connected three line to neutral or line to line voltages, or do we have only two line to line voltages connected. In case you want to use U4 channel for AVR function, you will need to set that to SS mode, which stands for system set. After this, you just set up what is the voltage transformer primary and secondary nominal voltage, and in case you are using the U4 channel, you also set the same for that channel as well. When that is done, we go to frequency, and here we set up the system nominal frequency. Is it 50, is it 60, or maybe in some cases something else. Then we choose three reference points for frequency sampling. And here I would say that it's good to have one or two, maybe two voltage channels as the reference. So in this case now we have the first and the second voltage channel as the reference. And then as a backup we have one current channel as the reference in case these two are lost. Then we move on to enable the AVR function. So we go to control and controls enabled. Here we have VReg AVR mode. Set that to activated. Once that is activated, we can go to control functions, and now this function is visible here. So the first thing that we set up here is the voltage measurement channel. So which is the voltage that this function is monitoring. And in case you are using the U4 channel, then you would set that one, and then you would choose which voltage is connected to that. So next we set up the target voltage and a control window. And this is done at the settings tab. There we start by setting the target voltage, and in this example we have set it to 102.5%. So this is now in relation to the voltage transformer that we set up earlier. So in this case, it would be 20 kV multiplied by 102.5%. Then we have taken the first voltage window into use, and for both overvoltage and undervoltage we have set up the same 2% as the limit. So this means that overvoltage picks up at 102.5 plus 2%, which is 104.5%. And undervoltage, on the other hand, picks up at 100.5% because it's 102.5% minus 2%. In the first window, both over and under voltage, they use the same time delay. There are a couple of basic rules that apply to setting the first voltage window. The first one is that the window should never be set below the value of the tap step effect. Tap step effect means that how much does the voltage change with each step in the tap changer up and down. And the window should never exceed the allowed variation loads. So therefore, the minimum voltage window size can be calculated like this. We take that tap step effect, again, how much does the voltage increase or decrease every time that we increase or decrease the winding in the tap changer, and then we multiply it with 1.2. So this gives us 20% more dead band for total band for regulating, and this ensures that the voltage remains within the voltage window after tap change operation. You can increase the regulator sensitivity with a smaller window, but this is not really advised, and here are a couple of examples to show why. In this example situation, the window is smaller than the tap step effect. And as you see, when the voltage goes over the limit, you will get the command, and it will just go right over to the undervoltage side, and then you will get the increase command, and it will go to overvoltage side, and so on and so on. And maybe at some point it will reach the window, but this doesn't really improve the network voltage quality. Here, on the other hand, the window is exactly the same size as the tap step effect. It's a little bit better, but still not really much of an improvement. As you see, it just doesn't really improve much. It's better than the previous one, but when we start to get somewhere to 1.2 times tap step effect, it's starting to stay in a pretty good position. So the second stage otherwise functions in the same way as the first voltage stage, but there is an option also for definite and inverse time delays. The second stage should be the first stage setting plus one step effect. If inverse time mode is chosen, it will use the formula shown here. So for example, if you have set the time delay to 40 seconds and the measured voltage difference from the set target is 4%, the time delay will be 10 seconds, which comes from 40 seconds divided by 4. So when defining the setting limits for the second faster operation voltage window, you must ensure that the one-step tap change cannot bring the voltage within this first voltage window. So in this example, we have set up the first voltage window to 1.2 times tap step effect, and then we have added 2 steps, so 1 step to both sides. So when the voltage exceeds this higher limit, you will get a voltage lower command, and it goes under this second window but stays over this first voltage window. And then we get a second control, and then we have the voltage inside the first voltage window. There is also overvoltage overvoltage states for instant operation, the third stage, and also undervoltage blocking setting. So when the voltage goes under this setting, the function will stop producing voltage raise commands. If you set this to 0%, blocking is no longer in use. And there's also internal overcurrent blocking that you can also enable, which can be used for blocking the function from compensating for voltage drops when a transformer is under heavy overcurrent. So when you have very high overvoltage, the regulator instantly lowers the voltage without any other delays but the given minimum time between the control pulses. So this lowering function remains in use until the measured voltage is below the set instant low threshold level. So then the low voltage blocking, so you use this to prevent the tap changer operation to avoid the control to the maximum position when the feeding voltage returns to the nominal level. So this can occur in various power-off situations, such as when there is a heavy short circuit fault in the feeding network side, or when the tap drifts towards the maximum voltage. So the recommended setting for this low voltage blocking is the maximum tap increase positions effect. So for example, if the tap changer has plus minus 9 steps times the tap step effect, which in this example is 1.67%, we get 15% as the setting. Then we move on to the actual control commands. So we go to the I/O page, and there we have direct output control, and then we simply choose which of the digital outputs are then closed when raise tap command and lower tap command are given. Then when those are set up, we want to set up the control pulse timing settings in case these need to be changed from the defaults. So all control pulses are at least as long as the pulse length minimum. But if the function doesn't detect tap position change before this pulse length maximum has been reached, then it terminates the control signal. And then the function always waits this minimum time between pulses before producing another command. Even though it's called automatic voltage regulator, this function can also be set to manual mode. So you can give manual tap raise and lower commands yourself. This can be done by going first to the I/O page, and there we have input signal control tab, and there we have this point AVR to manual control. So to this one you can set some digital input that is then maybe connected to some kind of like a switch or a button, but this is not really advised in case you want to use some remote connection to change between automatic and manual control modes. In case you want to do that too, I would suggest using the so-called programmable control switches. The advantage of that is that you can control this point both locally from the relays panel and also remotely through some SCADA communication like IEC 61850, Modbus SPA, or any other communication protocol that you might be using. So we click on Edit on the AVR to manual control, and then we can use this search function to search for a switch. We have 5 switches here, and choose one of those. And if you want to change the name of that, you can do that at Control, Device I/O, and Programmable Control Switches. Then, if we are setting up AQ-210 series unit, we go to AQ-200 Mimic Editor, which is at Tools and Mimic Editor, and then we choose just one block from the grid, and then choose one of the switches from the window that pops up, and then we choose another block in the grid, and then we choose this VRG object. So now basically everything required for switching between automatic and manual mode is done. This VRG object over here, it has an internal connection to the automatic voltage regulator function, so you don't need to set up anything more. Like even though you see these kinds of points here, you don't need to put anything to these. Those are just if you are going to connect some kind of digital input or other binary signal to those points to control up and down. So then when you have those points in the mimic, you can control these points by pressing this control button until a cursor appears around either of these. So first you would put the cursor over this automatic manual mode switch, and then when that is highlighted, you can activate manual mode by pressing 1 or disable it by pressing 0. And then when it's in manual mode, by pressing the control button, it will eventually go around this up and down arrow, and then by pressing 1 or 0, you will give raise or lower commands to the tab changer. And both of these points can be then controlled through SCADA remotely. When you're configuring AQ-250 series device, you go to Tools and 250 Mimic Editor. You right-click on Add Item, and then choose From Library and choose this control button Automatic Manual. You choose the programmable control switch that you connected previously in the voltage regulator function page. And then for that same button, you choose first that auto.png image, and then below in the list you will choose the same switch so that this picture follows the status of that switch, and the same thing for manual.png image. Choose the same switch, so then it will show the correct image. In the AQ-250 Mimic library, there is also an object for controlling the tap. It works in the same way as in the AQ-210 series. But if you want to make a tap control object with a custom image that you have made yourself, you can add an item, then you add an image, enable write object over here, and then remote tap control inputs to raise and lower. But an alternative method in the 250 series is that you could use the function buttons that are on the right side of the device. To do this, you go back to that voltage regulator function, and in the I/O page, input signal control, below manual control, you have manual raise and manual lower points. And to these, you choose status push button 1, 2, 3, 4, 5, whichever you want to connect to that. Choose the on signal. Then it's a good idea to also choose, or it's a good idea to guide the user on what buttons do by adding text to the mimic view. And then next up is how to set the tap changer position indication. And first we are going to choose the indication source. Currently the function supports these following position indication sources. The milliamp input, which is by far the most commonly used method. Then there are also binary coded and BCD, which is binary coded decimal inputs that are done with digital inputs. Digital input voltage channels can also be used for measuring the tap changer position. And then resistance can be also measured with RTD channels in the RTD option card. And this position, when you have set it up, you can see it in both Mimic and SCADA. First, we start with milliamp inputs. There are many ways how to get milliamp input measurements to 200 series devices. The first one is RTD input option card. And in this one, the last two channels also have milliamp inputs. Then there is a milliamp output card, which has 4 milliamp output channels and then also 1 milliamp input channel. And then also there is a possibility to connect this external ADAM unit that connects to RS485 port. So to choose the milliamp inputs, there are a number of selections. Let's go to Activate side and to Info page. There we have tap settings in the Info page. And here we have milliamp internal input 7 and 8, which are the ones included in the RTD card. Then we have external inputs, which is ADAM unit. And then we have milliamp input 1 and milliamp input 2 in I card 1 and I card 2. So if we have 1 or 2 milliamp output cards, those are the channels here. Then when we have selected a milliamp input channel, then we set the total amount of steps, and then what is the center position of those steps. So in this example, 18 and 9. This setting is used for setting the milliamp input together with this milliamp input low range and high range, and these tap steps totally. It will then put all of the tap positions in this between this minimum and maximum range of the milliamp measurements. There are two ways to indicate the tap position location. Normally the steps start from 0 and count up to the maximum value, so starts from 0, 1, 2, 3 and goes all the way up to 18 in this example case. But alternatively, the steps can be indicated relative to the center position, like in this image here. This is called a tab location now. So in this case, the tabs would actually start from -9 and go up to 0, which is then the central location, and then go again to +9. In some rare occasions, the tab position actually works in a reverse order, which means that 4 milliamps actually means tab position 18, or the maximum position, and then the maximum milliamp value is actually the minimum position, so 0 position. This can be changed by using the tab position indication parameter. Change that from minimum milliamp maximum position to minimum milliamp to is a maximum position. And unfortunately, a lot of the times the milliamp signal coming from the tab changer isn't linear at all. So if that is the case, what can happen is that when you are changing the tab position, you might notice that in the relay side you don't see any change in the tab position when it has actually changed one step, or then you see it change 2 steps when in fact it has gone only 1 step up or down. This can be changed or fixed by using a scaled curve, and you do this by going to Measurements and Analog Scaling menu. There you activate Analog Input Scaling and one scaling curve. Then you select one of the milliamp inputs. Then in the same page, you activate a few points for the curve, and then select the input value and what is the corresponding output value, in this case the position. So first set up the maximum and minimum value, and then add one or more points in between those minimum and maximum values. Then once this has been set up, go back to the voltage regulator function, and where you would normally choose a milliamp input channel, you instead choose a scaled input and then choose one of the curves that you have just set up. Position indication with digital inputs. This one can be done if you are using binary coded inputs or BCD inputs, which stand for binary coded decimal inputs. And in addition to those two, there's also the possibility to take a voltage signal from the tab changer and connect that to one of the digital inputs. And because the digital inputs in the digital input option card, they are able to measure voltage as well. Binary coded inputs and BCD inputs, they both use digital input statuses to determine the position of the tab changer. The two modes are otherwise working in the same way, but the difference is in how the modes use the digital inputs to report the tab position. And as you see here, in the binary coded inputs, it just uses the basic logic in the binary codes and goes all the way up to 31. But when you're looking at binary coded decimal inputs, you will see that when it reaches number 9, which is 1001, the next number 10 isn't actually 1010, but it goes to the next binary or the next bit. So number 10 actually is 10000. So otherwise they are the same, but BCD inputs use this kind of logic. And for this one, you can use the digital inputs in the CPU card and also the digital inputs in the option card. So to use either of these, you select binary coded inputs or BCD inputs like you would with the milliamp inputs. And then once you have selected either of those, you go to the I/O page and input signal control. There you will see all of the 5 bits available for the binary inputs. So then you just click edit and select the digital input referring to each of the bits. And then using the voltage measurement of digital input channels in the option cards. To do this, you will have to go to measurements and analog input scaling, and there you activate analog input scaling. You activate one scaling curve and then select one of the voltages. One thing to note though is that you cannot choose nowadays these digital input 1, 2 and 3 voltages, because these do not measure voltages anymore. It's only these digital input option cards that are able to measure voltage. Then you set 2 or more points to set the voltage range, which voltage is which step. And then when that one is set up, you go back to the voltage regulator function and choose a scaled input as the position indication, and then choose that curve that you just set up. And RTD measurement channels can also be used if you can get resistance as the signal from the tap changer. So you basically use the same steps as with digital input voltage measurement. Activate analog input scaling, activate a curve, and then choose one of the channels, and then you set up what resistance refers to what step. So those were all of the most important things when setting up automatic voltage regulator. Any questions you might have, you can send over in the chat box, or then you can also contact our technical support. You will find a link to our support portal at our website, arcteq.fi. Thank you for your time. Check out other videos that we have on our YouTube channel, and have a good day.